Section 3.2 finds us continuing on our function journey, and it's more information about functions. And remember, if something is a function, that means every value in the domain, the input, gives us one value out in the range, the output. So our objectives today is basically being able to analyze functions in even more detail. There's a section coming up, I believe it's in the next unit, where we're going to tie all of this together, and you can see how all of these pieces fit together. Right now we're still kind of collecting the pieces, but eventually I promise we'll put it all together and you'll see why we're doing all of these pieces. So the first thing we're going to talk about is being able to tell where is a function increasing and decreasing. If you are ever planning on taking calculus, this is a big deal in the calculus world. We're very much concerned with, okay, where is something growing or increasing, or where are we losing value, or where are we decreasing? So on this visual that I have over here, I want you to think of kind of like you're traveling on a road. You're going to start on the left, and you're just going to travel from left to right. So notice as I travel from left to right, I am physically going lower. So that means we are decreasing. And then it's like, once I pass this point, I change what I'm doing. And now I'm horizontal, constant. I wasn't going up or going down. And then once I pass that point, I am now going up or gaining value. So how we would write that if I had to describe this to someone, if someone said, hey, where was it decreasing? We would first say, well, we were decreasing from -2 until 0. We use the x's. And the reason why we use the x's is because we were literally going left to right. So if you draw a vertical line here, think between x is -2 and x is 0, my graph was falling. And that's what this means. They will always use parentheses. If you use brackets, I won't count off. The parentheses or brackets don't really matter on these because I'm more concerned with what's happening in between. I don't really care what's happening at the values. So then if I want to talk about where was it constant, well, if you look at my yellow vertical bars here, we were constant between 0 and 2. Again, we're using the x's. So from x is 0 to x is 2, I didn't go up or down. And then if I want to talk about where was the function increasing, if I draw in another bar, I don't know if these yellow bars will help you, but sometimes it helps students to visualize, okay, from here to here, my graph was going up. And it's a reminder that we're using the x's. So from 2 to 4, my graph was increasing. So we're just looking at it visually and then putting it into terms of intervals. Let's try some examples. So use the graphs to describe the increasing, decreasing, or constant behavior of each function. Now, one thing I forgot to add on here that I would like you to add before we do these should have arrows, meaning they're going to keep going. So please draw in the arrows. Okay, so let's look at this first graph. As I move left to right, what is the graph doing? Physically, what are we doing? We're going up, and I'm still going up, and I'm still going up. So this whole graph was going up the entire time. And you might say, well, wait, wasn't it constant right there? They will make it very clear if it's constant. You will have a flat horizontal line. So this graph was going up the entire time. So what we would say, we were increasing, well, from what x to what x? Because this graph keeps going on either end, we would say we're increasing forever. Forever from left to right. Keeps going. Okay, let's look at the next one. So as I come in from the left, we should see, oh, we're increasing. And now once I get to this point, I'm going to change direction. So I'm going to kind of put a wall there. So I'm going to say we were increasing. We have to talk about the x's. Now notice this arrow. So we were increasing from negative infinity to negative 1. Think about that. Because if I extended this, it's like I'm coming in from the left forever until I get to this wall, which is at x equals negative 1. Now if I look at what's going to happen, once I pass x equals negative 1, the graph is falling until I get to this point. So I'm going to draw in a wall. So we would say we're decreasing from what x to what x. Look at my walls, my yellow walls. From negative 1 to 1, the graph was falling. And then after that yellow wall, the graph is going up again. So that's another increasing interval. From what x to what x? Well, I left off at the wall, so that's going to be from 1, and then it keeps going forever, so to infinity. Between them, you can put the or symbol, meaning this or this. So I had 2 intervals for increasing and 1 area where I was decreasing. Let's look at the next one. So as I come in from the left, I am increasing first. I draw in until I hit this wall right here. So from what x to what x was the graph going up? Well, because of this arrow, negative infinity until, people are tempted to say 1, but remember, where is the wall? The wall is at 0. It's the x values we're using, not the y's. Okay, then I'm horizontal until I hit this point. So that's going to be constant from x is 0 to x is 2. I didn't go up or down. And then after that, it's a different color here, the graph is headed down. So we would be decreasing from what x to what x? Well, I left off at x is 2, and now it's infinity, and people say, wait, shouldn't it be negative infinity? Again, we're doing the x's, so do you agree that after 2, the graph would keep falling? As I continue to move to the right, the graph is falling. That's what this means. From 2 onwards, the graph is falling. So that's why I'm saying infinity. As my x's get bigger, the graph is falling. The next thing I want to look at is being able to find, they're called min and max values. This is also really important in calculus, as well as some applications that we're going to do in here. We're often concerned with finding the largest or smallest value. So a min and a max I want you to think of as a hill, and a min, I want you to think of that as like a valley. So you can see on this picture, I have a minimum, minimum, maximum, maximum. When you see these words maxima and minima, that's the plural form, more than one. And the reason why the word relative is in front of them, there's something called an absolute max or min. Those are like the highest and the lowest points. Relative max and mins, they are literally hills and valleys. They don't have to be the highest. So like as long as it's making a hill, that's a relative max. I don't care that one is higher than the other. They're both relative maxes. So here's how we answer this. Let's say the ordered pair of this hill, let's say it was 7, 5. That's where it was located. So like I went over 7 and then up 5. We would say we have a relative max of 5. I'm 5 up, that's the maximum, and it's located at x equals 7. So when x was 7, I had a height or a max of 5. Okay, it would be wrong if you told me the maximum was 7. I didn't go 7 up. 7 is where it's located. That's how far over I went. Let's try it. Find the numbers at which f has a relative maximum or minimum, and what are the maximum and minimum. So let's do, it's kind of hard to see, but this point right here, is that a max or a min? You should say we have a relative min because it's a valley, it's a low point, and it's a relative min of how much? How far down is it? -1, and it's located at x equals -3. That's where it's located. The min itself is -1. Okay, let's do the next one. We have this high point. So that's a relative maximum of, how high is it? 2. And it's located when x is 0. And I do believe we have one more. It's over here on the right. That is a relative min because it's a valley. And how far down is it? -1. And it's located at x equals 3. So if I ask what is the min or max, I literally want to know its height. How high up or how far down is it? If I ask where is it, I want the x coordinate. The last big chunk that we're going to talk about with functions is on the word symmetry. If you think of like in art, symmetry, or if something is symmetrical, that means it's the same on both sides. It's like a mirror image. There are 3 types of symmetry that functions can have: x-axis, y-axis, or origin. So let's look at the pictures here first. If something has x-axis symmetry, that means, here's one piece, here's the other piece. If I flip the graph over the x-axis, the horizontal axis, it should match up with itself. That's like my mirror. It's a mirror image on either side. If something has y-axis symmetry, that means if I flip it over the y-axis, it should match up to itself. And the last one is kind of the goofiest. If it has origin symmetry on a graph, here's the origin. 0, 0 is the origin. It's like it has both x and y-axis symmetry. So if you think about it, I'll do my best to draw this. If I took this piece and I reflected it over the x, it would look like this. And then if I took that blue piece and reflected it over the y, it would end up on itself. So origin symmetry, think of it as flip, flip. It has both. So now a way to tell what kind of symmetry we have, if you replace x with -x and you simplify and you get the same exact equation out, it has y-axis symmetry. Why does that work? Well, look at this. Like this point right here, if its ordered pair was -2, 1, if it has y-axis symmetry, then 2, 1 should also be on the graph. So what I'm saying by that above business is if you change the x and you still get the same y out, that's y-axis symmetry. If you replace x with -x and everything turns opposite, you get origin symmetry. And x-axis symmetry, I didn't put it up here, but I should have. If you replace y with negative y, and that gives us the same equation. Then you have x-axis symmetry. And if we look at this graph, if this ordered pair up here was 3, 2, well, for it to be down here, this ordered pair would have to be 3, negative 2. It's the y's that changed. And the last vocab that I'm going to give you today, if you see the words an even function or an odd function, it's just another way to classify functions. A function is even if it has y-axis symmetry. A function is odd if it has origin symmetry. A way to remember that, odd and origin both start with O. Sometimes that helps people. So it's just another way of saying, if I was told a function was even for its symmetry, I automatically know it's going to be a mirror image over the y-axis. So it's kind of a shortcut when it comes time to graph. So let's try this. Determine whether each function is even, odd, or neither. Then determine whether the function's graph is symmetric with the y-axis, the origin, or neither. So there's a couple of ways you can do this, and I'll let you in on some shortcuts. First off, if you want to tell if it's even, odd, or neither just by looking at it, if it's a polynomial, if you look at all the exponents, so we have a 3 and technically there's a 1, if all of the exponents are odd, then this is an odd function. And we know then if it's an odd function, that means it has origin symmetry. Which if I had to graph it, it would give me an idea of what the graph could look like. Now, if you wanted to check this algebraically, according to odd functions, if I replace x with negative x, I should get the opposite equation. Here's what I mean by that. So I'm going to take my function, and I'm going to replace all the x's with a negative x. And I'm going to simplify. So this first guy, negative x cubed, that means negative x times negative x times negative x. So negative x times negative x is positive x squared times another negative x would be negative x cubed. Negative 6 times negative x would be plus 6x. So notice, look at this result and look at the original. See how everything turned opposite? That means it is origin symmetry, or odd. Think odd, opposite, origin, they all kind of go together. The next one, if I want to use my shortcut, if I look at the highest exponents, or all the exponents, I should say, they're all even. So this is an even function, which according to my chart means it would have y-axis symmetry. If I wanted to double check this, watch what happens if I replace the x's with a negative x. So this would mean negative x times negative x times negative x times negative x. Well, if you multiplied those together, you would get a positive x to the fourth. And back here, I would have to do my exponent first, so negative x squared would be x squared, and then times the negative 2. Notice, after simplifying, I have the same exact equation. So that means it's even, or it has y-axis symmetry. Now this last guy, if I look at the exponents, I have a 2, I have a 1, and then nothing. See how there's a mixture of even and odd exponents? If that happens, it means it's neither even or odd, because I had a mixture of exponents. If I wanted to check this algebraically, what I would see If I did my simplifying, a negative x times a negative x would be x squared minus 2x plus 1. If I compare this to the original, some things turned opposite, but not all of them. Because it didn't either all stay the same or it didn't all change, that's another indicator that this is neither even or odd. Again, these are pieces that down the road are going to help us make graphs a little quicker, knowing what kind of symmetry it has. Look at this example. Determine whether the graph is the graph of an even function, an odd function, or a function that is neither even or odd. Well, if they give you the graph, this is even easier. What kind of symmetry does this graph have? You should say y-axis, because it's a perfect mirror image on either side of the y-axis. So if it has y-axis symmetry, then that means this is an even function. And it's done. The last thing I want to look at, we'll see these boogers kind of come into play here and there. Piecewise functions. These are some of the most intimidating looking things in math, but they are some of the easiest things to work with. Literally, a piecewise function is made up of pieces. So it's two or more functions, but for different intervals. It's kind of like, think of it as if you've ever had to go to the post office and mail something, they'll say, oh, if your package weighs from here to here, this could be the fee that you pay to mail it. If your package weighs from here to here, then this is your fee. So there's different fees per weights. That's kind of what's going on here with this example. So I would use the function 4 times t if my input is between 0 and 15. I would use the function 60 if my input is between 15 and 240. And I would use the input negative 6t plus 1500 if my input was between 240 and 250. So the first thing it wants me to find is v of 5. So remember this function notation, this 5 is sitting in place of t. So this is basically saying when t equals 5, what do we get out? So I want to plug 5 in. So the question is, which of these three functions would I plug 5 into? Well, look at the input intervals over here. 5 is between which set of numbers? You should say, oh, it's between 0 and 15. So because 5 is between 0 and 15, I'm going to use the top function. So 4, and I'm going to plug 5 in. So v of 5 comes out to 20, and that is my value. Next one, v of 15. So they want to know when t equals 15, what would I get out? So let's look at our intervals. Now there's an issue. 2 of them mention 15, but I'm only going to use one of them. How do you know which one to use if they both mention 15? Well, notice the top one has the equal to bar. I can be equal to 15. The middle one, I can't be equal to 15. So because of that equal to bar, I'm going to use the top function again. So 4, and this time I'm plugging in 15. 4 times 15. And I'd get 60. And now look at the last thing they want, v of 245. So where does 245 land? Well, it lands in the third interval, so I'm going to use the third function. So negative 6 times 245 plus 1500. So I want to do my multiplying and my adding, and if you do that right, you should get 30. Real quick, I want to add one in that's not in here. What if I would have asked for v of 20? So if we look, which interval does 20 fall into? It's the middle one. 20 is between 15 and 240. So I have to use the middle function. So 60, well, there's no t to plug my 20 into. How do I do that then? Well, that means the answer is always 60 for that one. There's nothing to plug into. And that's all there is to a piecewise function. You will always just use one of the pieces.